Hello and welcome. My name is Michael Horn. It is a beautiful sunny Tuesday, as you can see, and today we'll be learning a little bit of separation processes homework. This first video will be the completion of part A for homework 3, and I will read you a little bit about what we were doing. Today we're going to draw the schematics for the rectifying, stripping, and feed sections of a distillation column with a total condenser. Then for material balances around envelopes of these column sections, we're going to derive equations for the rectifying/stripping operating lines and the Q line for the feed. So we're going to work through this step by step and explain every part of the process so both the viewer and myself completely and thoroughly understands how this process is completed. So the first thing that we're going to do, like as I mentioned, is the rectifying portion. And to do this, we're going to have to design a distillation column. So here I will draw a rectangle and I will label this distillation column. And now it is important to remember that inside this distillation column there's going to be a series of trays as shown. And so now the next portion that we're going to scribe down into this is that there are going to be two portions inside this distillation column. The first being the liquid, which I will draw in blue, is dropping. And then our vapor in red is going to be rising. And so for this specific portion, the rectifying portion, we're going to highlight specifically the vapor. Now the whole purpose of this rectifying is so that we're actually going to run it through a condenser. So I'll move this, and as we mentioned, we're focused on this vapor that is rising. So all of this vapor that comes up, we'll label it V, is going to go into this, which I will label as condenser. And then the output stream is going to be completely new. So we have a certain amount of liquid, coming back, and then we also have the second output over here. And as you can see here, this purple arrow over to the right, this is actually our in the real world this would be our distillate, which is just a fancy way of saying that's our desired product. And so this, I'm going to use my laser, this leftover portion that is going back into the distillation column, that is our still liquid that we did not want in our distillate, and so that's why we will continuously run it through that distillation column using the liquid that drops, which will create a vapor that rises when we boil it off, take that boiled off vapor into the condenser and continuously create that distillate. So now we will actually be able to get into the material balance portion of this. And so before we do that, we want to label some things. I'll do this in red. So this is 1, 2, 3, 4, 5, and N. This can go as many sections as you want, so that's why we use this N value. And then we want to first write our equation, which is our vapor is going to be equal to the liquid plus our distillate. And so now we will use these labels above to rewrite the equation, which we have y times, or sub n plus 1 times v is going to equal x sub n l plus x sub n d. And then we are able to plug in that previous equation, and you arrive at y sub n plus 1 times liquid plus distillate equals xnl plus xn distillate. I do want to note one thing. I did make a mistake here. I did just fix it. This is not x sub n, it's x sub d, both there and there. And so now I'm going to kind of hand wave over the algebra for the sake of time. And you come to arrive at your final equation, which is y sub n plus 1, well, equals your liquid over your liquid plus distillate, that all times your x sub n value, plus your distillate over your liquid plus distillate, and that all times xd. The next key or important thing that I'm going to mention is a term called reflux. Now, what is reflux, you may ask? Reflux is going to be the proportion of our distillate to our liquid. So it's going to essentially be telling us how much of our distillate we're actually pulling out of the total concentration to see what our ratio is from of our wanted product versus the product that we don't necessarily want. Even though we are recycling it, we still don't want to have a high concentration of that. So as I mentioned, the equation for that is going to be liquid over distillate. So now we will be finding the operating line equation for our rectifying portion. And so as I just mentioned, we have this reflux equation and we want to sub this into here. Now to do this, after you kind of complete all of your algebra, as I said, I'm going to skip that part just to avoid mistakes and save time. You get y sub n plus 1 equals r over r plus 1 times the value xn plus r over same fraction r plus 1, this all times xd. Now I will kind of put a box around this. I will label it. On. There we go. I'm going to label this rectif. So now we've completed the rectifying portion of this, and again, I will just give you a little bit of an overview. So we started with this distillation column with our trays, and we are looking at the vapor in this situation. So as I said, as the liquid drops, we're going to boil off the vapor into this condenser. The product of the condenser is going to be a mixture of liquid and distillate, and that liquid to distillate ratio is considered our reflux. And so after creating this equation right here, we are able to plug reflux in and arrive at this rectifying equation highlighted in green. And now we are able to continue into the stripping portion of this video. And so for the stripping section, we again are going to create a distillation column, in which I will draw again. And now, as I mentioned before, there are these trays in the column. But instead of looking at our vapor that was being boiled off, this camera keeps like focusing terribly. I keep trying to like fix it. Okay, I think it's okay. Anyway, so instead of looking at our vapor that is being boiled off into the condenser, this time we're going to be looking at our liquid that is coming out. So we'll draw an arrow here and label this our liquid. And so this process is going to be kind of the inverse of what we did above. And so I kind of got a little bit ahead of myself here. We're going to delete this. We still are going to have this liquid coming out, but there's going to be a heat exchanger kind of interrupting that process, just like we had the condenser, above. And so there's going to be liquid coming out of the heat condenser, but then we're also going to have that vapor going back in. And so as you can see, I labeled it. We're going to have our boilant coming off. Previously we had our distillate. This is called our boilant. And then we have our reboiler and our vapor. And so this time we're going to want to label things again. And this time we have 6, 7, 8, 9, all the way down to N. And so now we are able to actually do our material balance, which I will write.
Liquid equals our boilant plus our vapor, or in this case it is V bar.
And so let's begin writing that equation. So we start with our liquid, and that is going to be equal to our boilant plus our V bar, which is associated with our vapor. And then like we did previously, we're going to break that down into the actual components, which is Xn liquid times Xb, which is the concentration of our boilant, plus Yn plus 1 times V bar. And then again, we can plug that into each other, in which you arrive at the equation Xn times B plus V bar equals Xb times B plus Yn plus 1 times V bar. And so now, as we did previously, we're going to take this a step further in completing this algebra, and we want this Yn plus 1 to be completely isolated. And so after you do this, I'll make this bigger, Yn plus 1, you're going to get xn times b plus v bar minus xb times b, and this will all be divided by v bar. Now you can't forget that again, as we had the reflux from the past equation, we are going to have a variable of VB now. And this VB is going to be the ratio of our vapor to our boilant. And so now we are just one algebraic step from finding our operating line equation for our stripping section. And so we plug in this VB value into this equation above, and you arrive at y, n plus 1, is going to equal 1 plus VB over VB, all of this times our xn value, and then subtracted, we will have 1 over VB, all times our xb value. So again, I will put this in a little box and write stripping. And so now I want you to kind of pay attention here to the overlap in what we did. So the diagrams are essentially inversed. The first one we were looking at our vapor, and then using that calculated ratio of our leftover liquid to distillate and finding our equation, as you can see here. And we have this variable called reflux here that we're able to sub into to find this rectifying. And then down here we do kind of the same thing. We're finding the ratio of our leftover vapor to our boilant and subbing that in. So it's a very, very similar process to the first one, just with different variables and a kind of an inverted diagram, as you can see here. And so now we were able to go into the last portion. So now we have reached the feed section, and this diagram is going to be a little bit different than the previous one, but it is still going to have a distillation column. So we draw our little square distillation column. And then in this top portion, as we saw above, we have liquid here, and then we have liquid here. And the way that we know this is from our top two. In our first one, you can see we have that vapor leaving and the liquid coming in. And then in that second one, we have vapor coming in and liquid leaving. So that is our diagram. And so now we're going to use those two equations that we found earlier, and we will write them next to this because we are going to use them. And so our first is our stripping section, in which that is xn L bar equals xb times our boilant plus y n plus 1 v bar. And then we will also have y n plus 1 v equals xnl plus xd times our distillate. And I will label this. This is our stripping section, and this is our rectifying section. Let's move this over a little bit. That's better. So the next portion of this is going to be kind of reflecting on some of the work we did back a couple years ago in MEB, in which you're able to kind of draw a dotted line around which section of the diagram to actually create an equation. And so we're going to combine the two diagrams that we've done before. So we have, this is just kind of a mini version of our distillate column. So we have that. And then as you know, we have this feed coming out. Sorry, first we'll actually draw. Oh. My thing just glitched out. Hold on. Sorry about that. My iPad cast just shut off for some reason. So anyway, so as I said, we have our distillate column here. Then above we have our condenser. And then below here we have our heat exchanger. And so you're going to have our stream up here leading to this. We have our stream coming back here. And we also have our stream leaving the system. And same for here. We have our stream going into here. That's not what I want. We have our stream being recycled out. And we have our stream leaving. We also have our feed. So now, if you draw your dotted line around this to create your system, you would say, okay, well, I kind of want around there. I don't want to deal with any of the condensers. Okay, so when you look at this, you realize, okay, well, I only have, my 2 streams going out and 1 stream going in. And so now that we created this, system, we're able to actually get another equation. And this equation is now going to take the difference in our liquid and the difference in our vapor. And so you're going to have y times n plus 1 times v minus v bar is equal to xn times L minus L bar. And then this is where you kind of incorporate that stripping section, which you add your xb times the boilant plus xd times the distillate. So the next portion of this is kind of creating another variable in which we're going to label Q, which was the liquid fraction of our feed. So I'll kind of write that down. Liquid fraction of feed. That's going to be Q. And so then we can also write a new equation, which is Q times F, which is our feed, is going to be equal to L minus tau. We're also able to look at this in terms of our our vapor, which is 1 minus Q times F equals V minus V bar. And then now we are going to take this and kind of plug this into this algebraic equation we created. And so now we rewrite the equation above in terms of our feed, in which you get y sub n plus 1 times your feed value multiplied by 1 minus q is going to be equal to our xn value times q times the feed plus our zf value times the feed. And when you look at this, you think, oh, well, everything's multiplied by f. We don't need that. You would be exactly right. So we can cross all these f's out. And so now the last step before we get our q line for the feed portion is to rewrite this again in algebraic. And the final equation you get is y sub n plus 1, and that's going to equal q over 1 minus q times x sub n plus 1 over 1 minus q, and then our feed. So I will square this off. And again, this is the q line of our feed. So I'll write feed here. So now just kind of a summary for everything. We kind of broke this down into 3 processes. We looked at the top, which is going to be our rectifying, looking at the distillate and the introduction of a condenser. And we get our rectifying equation here. Second, we look at the bottom portion of this distillate, which we have our boilant and our reboiler, or heat exchanger, whatever you prefer. And we get our stripping equation. And finally, when we look at the system as a whole, we get this algebraic equation in which we use our feed concentration value ZF, and we are finally able to arrive at our 3rd equation. Thank you for watching. This has been part A of homework 3 for separation processes, and I hope you're able to follow along. Thank you for watching.